All right, welcome everyone to today's seminar. Today we have two early career speakers who will be talking about solar wind and its influence on the magnetosphere and imaging the Earth's exosphere and cusp and magnetosheath regions. So our first speaker today is Nithin Sivadas. Nithin did his bachelor's and master's degree in aerospace engineering at the India Institute of Technology, Madras. He then joined the PhD program at Boston University, where he worked on studying the sources and effects of energetic electron precipitation. At BU, he was awarded the NASA Earth and Space Science Fellowship and graduated in 2020. Since then, he has been working as a postdoctoral research at NASA Goddard Space Flight Center, studying how the solar wind uncertainty can affect space physics studies. Nithin, with that, if you'd like to take it away.
Thank you, Kyle. So I will get on with this talk. I've tried to make it short so that if anybody has questions, we have room to have a little bit of a discussion at the end if we want. So in heliophysics, there is significant interest in understanding how the sun and the solar wind impact the planetary space environments, in particular the space environment around our planet, the Earth. So in fact, there is a lot more to study with regard to how extreme space weather affects our planet. Last year, we had this SpaceX launch failure where they lost 40 out of 49 satellites due to severe space weather that we did not necessarily anticipate and its effects on atmospheric drag. So extreme space weather can cause many other sorts of disruptions, communication disruptions. It can impact gas pipelines and power grids on the surface of our planet. So the study of how the Earth system responds to space weather is a crucial one in the field of heliophysics. However, there is one major challenge that haunts most of our investigations into the effect of the solar wind on Earth. We are uncertain about the solar wind that actually drives the magnetosphere system around the Earth. So when we talk about uncertainties in general, what comes to our mind is usually instrumental error. However, most of the error in reality is coming from assumptions that we make in using the measurements. So when we measure the solar wind parameters, we mostly do so far away, 230 radii upstream of the Earth at the L1 Lagrange point. So we do not have access to the solar wind parameters that actually drive the magnetic reconnection, which is much more closer to the magnetopause at the reconnection site. So we have to make certain assumptions to estimate the solar wind that impacts the magnetosphere from L1 measurements. So for example, we have to make assumptions about the solar wind propagation time. That is, how long does it take for the solar wind measured at L1 to reach the magnetopause? We have to make assumptions about the solar wind structure and the solar wind interaction with the intervening space between L1 and the magnetopause, where you have the bow shock, the magnetosheath is composed of a lot of plasma flows. So we usually neglect or consider the structure, and these interactions are not that greatly relevant to solar wind driving of the magnetosphere. But since these assumptions are not accurate, our estimates of what solar wind we think actually impacts the magnetosphere has some uncertainties. And my point of this talk is that even if these uncertainties are random, that is, our estimates of the solar wind impacting the magnetosphere is sometimes an underestimate and at other times an overestimate. Even if that is the case, we would be underestimating the response of the Earth's magnetosphere to the solar wind driving. And in this talk, I would like to explain why and how this is possible using a very simple thought experiment. So consider you are making a measurement of some physical process, which is a stochastic process with an underlying probability distribution that we call X. This random variable x, for simplicity, I assume has a normal Gaussian probability distribution. Now imagine there is another random variable w, which is dependent on x. Here I assume the dependency to be very simple. It is quite literally w is equal to x. And under this paradigm, if you measure w and you measure x, and if you do a scatter plot of w versus x, then you will see that all the data points lie in a straight line with a 45-degree slope, because in my thought experiment, w is equal to x. This is trivial and all is well and good. Now, if there is some uncertainty in w, that is uncertainty in the dependent variable, then these scatter plot points will spread along the vertical direction, right? So now if you ask the question, what is the average response of w, the dependent variable, for a given x value, the independent variable, you'd be actually doing a nonlinear regression. And this would allow you to average away the uncertainties in the dependent variable. So what you will get after averaging w for a given x is a straight line with a slope of 45 degrees. So you get back the relationship that we'd assume w equal to x. So this is what most of us expect. If there is unbiased uncertainty in a random variable, you can average that away and get back the true response of the system. So all is well. Now here is a twist to this story. Now, instead of adding uncertainty in the dependent variable w, if we assume the same average, if you assume the same uncertainty epsilon was present in the independent variable, then suddenly the average response of w for a given x appears to have a biased slope. In fact, a lower slope than the line of equality. This is a well-known phenomenon, and it's called regression dilution bias. And you'll see this especially if you're doing linear regression analysis and studying that. Now, this phenomenon has many manifestations. So if you look at the plot, the scatter points represent the joint probability distribution of w and x. The green dot in the center is the mean of this distribution. And as you can see, the straight line's slope is sort of bending towards the mean value of w. So this is also known as the regression to the mean effect. So, you can search it online and get more details of this. And this is a statistical effect caused by the uncertainty in x and the probability distribution underlying x. So we can correct for this biased slope to get back the true relationship w equal to x if you knew what the uncertainty is and what are the stochastic properties of x, the thing that you're measuring. And in this case, I've assumed x and w to be Gaussian and uncertainties are uncorrelated. So these are very simplistic assumptions, and we can do this correction easily. However, we know a lot of physical parameters in space physics are not Gaussian distributed ones, nor are the uncertainties stemming from our assumptions uncorrelated. So hence, when x is a log normally distributed process like this, it has a long tail, and like many solar wind parameters are log normally distributed, and the percentage of uncertainty increases with x, right? When this is the case, it makes the response of the dependent variable w to the independent variable x with these uncertainties and the statistical properties appear to vary non-linearly with x on average. So w may even appear to saturate on average with x, even though the true response ought to be the straight line where w is equal to x. So even if we don't necessarily follow this thought experiment, the interesting thing is that we can see this effect in real data from spacecrafts at L1. So we will dive into some of that real data. So think of this scenario. We have two spacecrafts, ACE and WIND, at the Lagrange point L1, 230 Earth radii upstream of the Earth in a halo orbit, trying to measure the solar wind. We can compare ACE and WIND measurements. And we know roughly that ACE and WIND ought to be measuring the similar solar wind. And so they should be related in a simple way. ACE and WIND measurements should be equal to each other under ideal circumstances on average. So take the example of density measurements of ACE versus WIND. When you plot that over several years, you will see quite a bit of scatter in the data points. Because even though ACE and WIND are trying to measure the same thing, they do not exactly measure the same solar wind parcel, as they are separated by some distance in its halo orbit. And in this comparison, you begin to see the same statistical bias we saw in the thought experiment. So ACE appears to measure a lower density than WIND on average, especially at extreme values of the density. Now, you might think, oh, maybe the ACE instrument is biased in comparison to WIND. So there are some ways to show that this is not just a result of systematic bias in plasma instruments in these devices. For example, you look at the low values where you have more, a lot more data points. There appears to be not much of a bias in the slope at all. The bias seems to appear during extreme values. And another way to show this is to reverse the dependent and the independent variable. Here, the dependent variable is the ACE measurement, and independent variable is the WIND measurement. And if you were to reverse the plot, you would see that, or you would conclude that WIND appears to measure a lower density on average at extreme values in comparison to ACE. And that would be contradictory to this plot. And that cannot happen if it was an instrumental bias or a systematic bias. It can only happen when it's a statistical bias. Here's another parameter, the interplanetary magnetic field component in the Z direction, which is important in driving magnetic reconnection in the day side. Here too, you see a similar statistical bias. So on average, WIND appears to measure a lower BZ value than ACE at extreme values. These effects are observed in many such solar wind parameters measured by ACE and WIND. Here's a more complex parameter that is prone to a lot more uncertainty in the ratio of Y, which is the ratio of Y and Z component of the interplanetary magnetic field. This ratio is a measure of the clock angle, another important parameter that drives magnetic reconnection on the day side. And as you can see, WIND and ACE measurements of this ratio is highly variable. They spread about a lot in this plot here. But on average, the WIND BY by BZ ratio estimates appear to saturate with increasing ACE BY by BC ratios at extreme values. We can go further and look at solar wind coupling functions. So this is the merging electric field, which is considered to be a measure of the energy coupling of the solar wind with the magnetosphere. So here we have a scatter plot of 20 years of data comparing ACE and WIND measurements. And WIND on average appears to see a smaller merging electric field when ACE sees extreme values of the merging electric field. So why does this happen? I'll do a few quick heuristic explanations, even though the initial thought experiment that we did is to demonstrate to you that it happens. It's useful to understand heuristically, what is the reason for this. So most of the measurements of the solar wind are low values of the solar wind, right? They are small and close to the mean of the parameters that you're measuring. There are only very few measurements that are extreme and high, okay? Because that is the nature of the particular parameters we are measuring. So if we have uncertainties in your measurements, then it is far more likely that the high values of the solar wind you're measuring is in reality smaller and closer to the mean, since the smaller values are just much more likely to occur in reality. Okay. Another way to explain the same thing is that ACE and wind are both instruments trying to measure the same thing. So if one instrument measures something very high or extreme, it is far more likely that the other is going to measure something small or closer to the mean, simply because the values of the solar wind parameters closer to the mean are just more likely to occur. So we can go a little bit more deeper and explain this in a graphical way and try to get a bit more clarity. So consider that you're attempting to measure some physical process, X, and that X has some probability distribution function. So some values of X are much more likely to occur in reality than others, which are rare and extreme, right? So under these circumstances, let's say you have an instrument, a device that you're going to use to make this measure this physical process to get an estimate of the true value. And let's say that physical process, the true value at this point that you're trying to measure is X equals 2. Okay. So when you try to make this measurement, your instrument has some uncertainty. So there is some spread in your measurement. All right. Now, similarly, if the physical process is X equal to 4 and you're trying to make a measurement, there will be some spread in the probability distribution such function. So your instrument might measure anything in between this region, right? It might not just see X equal to 4, it might see X equal to 6, it might see X equal to 1. And this is the likelihood that it will see. And this is based on the uncertainty in your measurement device. Okay. Now, if you're with me on this, here's the crucial point. Imagine that your instrument gives you the reading 3, X equals 3. Your instrument tells you that it is 3. Now, if you look at this red dot here, that red dot is the likelihood that your instrument is actually mistaking the physical process when it's at X equals 4 to be X equals 3, right? Similarly, this blue dot here is the likelihood that your instrument is misreading the physical process at X equal to 2 as X equal to 3. And the black dot here is the likelihood is that your instrument is actually measuring X equal to 3 as, X equal to 3, that your instrument is correct. So when you compare these likelihoods, you notice that if your instrument tells you X is equal to 3, then the chances that the true value is X equal to 2 is much more higher than the true value is X equals 3. So this is the fundamental problem. There is a bias whenever you can make a measurement of a stochastic process, a bias in the true value of the physical process you're trying to measure. And that true value is much more likely to be closer to the mean of the process that you're measuring than what your instrument is telling you or what you're inferring from your instrument. So now I want to come back to the title of my topic, like how sure are we about the magnetosphere's response to the solar wind driving? Okay. The planet Earth and the magnetosphere ionosphere system surrounding it is in a way a solar wind monitor itself. So it responds to the solar wind just like ACE and wind satellites are responding. One measure of the Earth's response is the cross-polar cap potential, which you can measure using ground-based magnetometers or low Earth orbiting satellites or low Earth orbiting satellites in the polar cap region. Okay. So the solar wind electric field drives the day-side magnetic field reconnection, and its effects are transmitted through equipotential magnetic field lines, leading to some convection in the polar cap ionosphere that corresponds to this cross-polar cap potential. And one reason why the cross-polar cap potential matters is because global models of the magnetosphere ionospheric system, which we use to predict the effects of space weather on our planet, uses the measurements of the polar cap potential to validate its predictions. So the main thing here is that the polar cap potential responds to the solar wind. That's my point. So the plot on the left here shows this polar cap potential measurements, proxy for it at least, on the vertical axis, varying with solar wind electric fields taken from Lagrange point L1 measurements. Okay. So at small values of the solar wind electric field, the potential appears to vary linearly. However, at extreme values, the solar wind, the polar cap potential appears to saturate with solar wind. So this is known as the polar cap potential saturation problem. But on the right-hand side, we have not used any data. Okay, we have constructed an error model, just like the thought experiments we discussed earlier, and where X is a synthetic solar wind electric field that has the stochastic properties of the real solar wind electric field, and some assumed uncertainty epsilon that is correlated with the solar wind electric field magnitude. Okay, it increases with the solar wind magnitude, and it has a particular function. So, and as you can see here, this model predicts that the average response of the magnetosphere is very similar to that observed in the data on the left that shows the polar cap potential saturation. It also predicts a very similar conditional probability distribution function as shown by the scatter, plot. The dots here is also similar to the scatter plot on the left-hand side. The left-hand side of the data, right-hand side is the error model or the thought experiment where we are conducting. So this is an indication that simply the uncertainty in the plasma parameters that actually affect the magnetosphere can lead to an appearance of a nonlinear response of the polar cap potential to the solar wind driving. So my main point here is that if we have uncertainty in an input to any system, okay, then it can lead to a misleading and statistically biased inference of the system response when you try to compare data of the input and output to the system. Hence, we need to be very careful calculating the uncertainties and factoring in the stochastic properties of what we are measuring to remove the statistical bias that appears in our inferences before we can really say what is the true response of a system. Okay, so here I have placed 3 QR codes that link to recent papers that we have written, which discuss the nature of this effect. I have presented in this talk in more detail, and how we can quantify and correct for the biases introduced by these uncertainties in our system's response. All right, that concludes what I have to say here today.
All right, thank you, Nithin, for a great talk. We do have one quick question from Eric. So do you think that, so I guess it's a clarification. Are you arguing that the cross-polar cap potential saturation is actually a statistical effect as opposed to a physical phenomenon?
So in this talk, I haven't yet completed that argument, but I've shown that there is a possibility that it is a statistical effect and not necessarily physical phenomena in the sense that reduces the polar cap potential. So yeah, I haven't made the full argument in this talk, but that is the argument I'm attempting to make in these papers. Yes.
So Krishna has another follow-up question. Krishna, I may need you to correct if I'm not asking the correct question. So for the exact effect, is it always necessary to do the same calculations that you've mentioned whenever you're dealing with real data? Um, is this, I guess maybe, is this something that you would see in all data then?
Yes. So this sort of effect you would see in a lot of data. The thing is that usually most of us, when we do this sort of study, we are focused on the mean values. We are more focused on the common measurements. And in those scenarios, this effect is not that high. This effect becomes important when you attempt to measure extreme values, when we attempt to develop theories about extreme values and rare values. And that's when this becomes prominent. And therefore, we need to do this sort of analysis of the uncertainty and the statistical properties and remove this effect. I hope that was useful.
Excellent. So we have a follow-up, we might have enough time, from Carlos Martinez. If there's a lack of saturation, and if this is true, what are the implications in current models that incorporate this effect? And that's a fairly broad question.
Yes, yes. So yeah, that is a fairly broad question. One thing I know is that there are models in which, they don't necessarily see the kind of saturation that is seen in some other models. So there are self-consistent model where is the saturation is not necessarily that prominent and is to a lesser degree. And it's also possible that once we actually completely do this uncertainty analysis and remove the bias, we see that there is some nonlinearities, but it may not be as strong of a saturation as we see. I mean, it need not be saturating, it may just be nonlinear or, with a slightly biased slope. But yeah, I don't yet comprehend the full impact of all this in all the different models. But I think it is an important question, Carlos.
All right, excellent. Thank you for the questions, and thank you again, Nithin, for a wonderful talk. So with that, we'll move on to Gonzalo, who will be following up Nithin today. So Gonzalo, if you'd like to take the screen. All right, perfect. So Gonzalo did his bachelor's degree in electrical engineering at the Pontifical Catholic University of Peru. He did his master's in computer science at the University of Central Florida, and then joined the PhD program in electrical engineering at the University of Illinois. There, he worked on developing tomographic techniques to estimate exospheric neutral densities, and has now been working as a postdoctoral researcher studying data-based models of the Earth's cusp and magnetosphere, and using his work that he did as a PhD student to apply to new observations which are currently being developed at Goddard Space Flight Center. So with that, Gonzalo, if you would like to take over.
Okay, thanks for the introduction, Kyle, and thank you for inviting me to give this talk. First of all, I want to thank my collaborators in this project, which are Hyun-Yu Connor, Jae-Won Jung, Brian Walsh, and David Sivek. So I'm going to start saying that this project is in support of the upcoming NASA's LEXI mission. LEXI stands for Lunar Environment Heliospheric X-ray Imager, and will be launched in 2024 to image the daytime magnetosphere in sub-X-rays from the moon. LEXI will be part of the NASA's Commercial Lunar Payload Services initiative that will contain other 9 instruments. And all of these instruments will land over the moon on board the Firefly Aerospace Blue Ghost lander. Here I'm showing an illustration of this lander. And all of those instruments will do investigations of the moon and from the moon. In this case, LEXI will be a wide field of view imager with a 9.1 by 9.1 degrees field of view that will measure the sub-X rays generated by the charge exchange between solar wind ions, specifically high charge state heavy ions, and exospheric neutral atoms. At Earth, the neutral atoms are specifically atomic hydrogen. So this is an example of this charge exchange interaction. In this case, the charge exchange is happening between a heavy ion, O7+, and a hydrogen atom. The heavy ions picks up electron from the hydrogen and produces this O6+ ion and a proton, but also produces a sub-X-ray photon. Now, as I said, this is just one example. And here, this plot shows the different emission lines for sub-X-rays generated by several heavy ions for specific solar wind conditions that are specified in this reference. Each line here corresponds to a different heavy ion that includes iron, carbon, oxygen, among others. Also, in the X-ray community, we usually use the electron volt to identify the photon instead of wavelengths. And I mentioned that because LEXI will observe sub-X-ray in the range of 100 eV to 2000 electrovolts. Finally, these sub-X-ray observations will serve to achieve LEXI's goal, which is to identify the dynamic properties of the magnetosheath and the magnetopause. So one of the main questions of the heliospheric community is to understand the day-side magnetic reconnection, because this is the main mechanism to transport energy, momentum, and flux from the solar wind to the terrestrial magnetosphere. Also, it is known that the day-side magnetic reconnection occurs in the magnetosphere, in the magnetopause. Therefore, investigation of the dynamics of the magnetopause through global imaging, as LEXI will do, will further our understanding of the response of the magnetic reconnection to different space weather conditions. Now, I'm going to talk about my project. Our project will use and will take in consideration that LEXI is over a circular orbit with a 60 RE geocentric radius, with a 20-day orbital period and with no inclination. So the lunar orbit has a 5 degrees inclination, but in our study, we will consider that the orbit is over the ecliptic plane. In this plot, I'm showing the circular orbit here in GSE coordinates in geocentric solar ecliptic. Also, the field of view of 9.9 by 9.9 degrees will be divided into pixels using an angular resolution of 0.25, which will yield a 37 by 37 pixels image. The integration time that we're going to use in these simulations is going to be 10 minutes. And also LEXI will start acquiring data of the day-side magnetosphere when it is located at a azimuthal angle equal to 39, and it will take data of the day-side magnetosheath for 6 days until it reaches the angle 117. So in this analysis, because we're going to do tomographic estimation, we have to use two-dimensional images. Those two-dimensional images are going to consider some realistic sources of contamination. So for that, we are going to first create an image, as you can see here in this panel A, which is basically a physical measurement of energy flux. This image will be multiplied by the sensor responsivity to be converted into counts, like the panel B. Also, the image will be contaminated by astrophysical sub-X-ray background, and all these results will be convoluted with the point spread function, which is inherent in any optical system to have this distorted image here. And additionally, we are going to include Poisson distributed shock noise. Every optical system, every imaging sensor, it's counting photons, and the counting process is basically a Poisson distributed random variable. Therefore, we need to include this Poisson distributed noise in the image. Now, the objective of this project that I'm presenting here is to use these two-dimensional images with this level of noise to reconstruct the three-dimensional structure of sub-X-ray emissivities near the magnetosheath region. And with the magnetosheath, try to investigate or try to identify what is the location of the magnetopause. So, and also we have a constraint, which is to use the minimum number of images. So, and I'm saying this because we cannot use the 6 days of data. That would be great, but unfortunately, the magnetosheath structure is not going to be constant during 6 days. So we are trying to evaluate if we can perform tomographic reconstructions with data taken in 1 hour or less than 1 hour, when we can consider that magnetosheath is, let's say, constant in its structure. So just to clarify what we want to reconstruct, we're going to reconstruct emissivities. The emissivity in this presentation is represented by the letter P. This P is created, as I said before, by the charge exchange interaction between neutrals and ions. And in this case, we have this formula that is simplified that as this expression. In this case, the alpha is an efficient factor that considers the cross-section of the charge exchange interaction. This NH is the hydrogen density, this is the proton density, and this is the relative velocity between the ions and the neutrals. Also, this alpha will contain the abundance of solar wind heavy ions with respect to the protons. So this alpha multiplied by this proton density will convert the value into the number of the density of the heavy ions. For doing this, we're going to use OpenGGCM MHD model to generate the proton density in the day-side magnetosphere. So for that, we have used these following parameters. So this is the solar wind density, solar wind velocity, and the interplanetary magnetic field that we have used for this specific proof of concept study. That is for the proton density. For the hydrogen density, we have used a spherically symmetric exosphere that has been specified by Connor and Carter in 2019. In this formula, we have this N0, which is the hydrogen density at 10 RE, and this R is the geocentric distance. So with these values and this formula, we can estimate the hydrogen density everywhere in the space. And also we adopt a value of alpha equal to this value here that has been specified by this author, Jorgensen et al. 2018. So with these values, we can generate the emissivity everywhere in the space. Of course, we are going to just do the analysis in the day-side magnetosphere. So for that, we have created a kind of region of interest with these dimensions. In the X dimension, it goes from 0 to 16. In the Y, it goes from -20 to 20 RE. And in the Z axis, it goes from -6 to 6 RE. The resolution for this emissivity is 0.1 RE. And what you can observe here is the ecliptic plane and the meridional plane. Of course, this is a three-dimensional structure, and in all my presentation, I'm going to show only these two planes, the ecliptic and the meridional planes. So I'm going to call this the ground truth because this is what we want to reconstruct. The values here are in units of electrovolts per cubic centimeters per second. And another term that I'm going to use in my presentation is the volume emission rate, which is similar to the emissivity. So the values that I have here are corresponding to the calculation using this formula. This is what I want to reconstruct. Now let's go to the technique. So the technique that I'm going to use is tomographic reconstruction. And in any tomographic technique, we need to have a kind of linear relationship between measurements and what we want to reconstruct, that in this case would be the emissivity. So fortunately, we have a linear emission model that is described by this equation here, in which this I is the measured intensity by an observer in the space. And I have this plot just to facilitate the structure of this equation. So here I have the observer, and this line of sight, this is a line of sight for a given pixel. So let's say LEXI will have 37 by 37 pixels. This line is just describing the observation of one of them. This N hat indicates the direction, and this line of sight is passing through the magnetosheath, which is represented by these three colors, red to yellow, and this is basically the emissivity. So when the line of sight passes through this region, it will capture the photons that are moving towards the observer. So that part is represented by this second term in the equation. But also the measurements are going to be contaminated by astrophysical soft-X-ray background. These soft-X-rays are going to be generated everywhere in the universe. It can come from interaction of solar wind with exosphere of other planets, and so on. In this case, and for our study, we're going to use just a constant value for astrophysical soft-X-ray background. Once we have this emission model, the idea of tomographic reconstruction is to discretize and convert this linear emission model into an algebraic form that looks like this. Something simple, something that we can operate with in a computer, and this is a kind of matrix vector operation. So how can we generate this problem that in a moment I'm going to say that is an inverse problem? So we have to make some steps, and I have here 3 steps, let's say 4 steps, because I'm going to include one more. The first step is to generate this vector of background free measurements. So for each measurement, what I'm going to do is subtract I minus this background, assuming that I know this measurement and I also will have information of the background. I subtract those two values, and I'm going to have the value of Y. This Y is a scalar, and if I have a set of measurements, like for example, in one image, I will have 37 by 37. I will create with all those measurements a column vector that will be called Y, and this ball Y. Then I will create the matrix L, which is called the observation matrix. And for that, I have to do an intermediate step. So that intermediate step is the discretization of the region of interest. So as I told you before, I'm interested in the day-side magnetosphere. So I'm going to discretize that space. So in this case, I have used a spherical sector as the region of interest, as you can observe here. This spherical sector has these dimensions. In the radial dimensions goes from 6 to 16, and the simular it goes from minus 90 degrees to 90 degrees, and in the polar, it goes from minus 35 to 35 degrees. Also, I have to divide and discretize this region of interest into spherical voxels. And the dimensions for those spherical voxels are given in this column. So now we can use any kind of structure. I'm using spherical voxels, but we can use cubes or we can use any other structure. I have used spherical voxels because that allows me to have a small number of voxels in all this region. So the way to use this information to generate the observation matrix is by intersecting the line of sights with the voxels. That intersection will create line sectors in each voxel, and that length it's going to be used to populate my L matrix. My L matrix has a size of n, which is the number of measurements, by n is the number of voxels, and each value will correspond to the intersection of a line of sight with the voxel. For this, I will need information of the satellite location, the line of sight direction, and the voxel size that is given here. At this point, I can have information from Y and from L. So just having the data of the position of LEXI and the images from LEXI, I can create Y and I can create the matrix L. So the only unknown is X. X will contain the information of the emissivities, the variable that I want to reconstruct, and those emissivities will be the values within the voxels. Something that I forgot to mention is that in each voxel, we will have an emissivity that will be constant around all that voxel. So this X is an n by 1 column vector of volumetric emissivities, and as it is said here, it's the only unknown. So the tomographic reconstruction technique probably ends at this point in which I generate this problem in which I have the Y, I have the L, but I don't have the X. So there are several techniques that allows me to solve this problem. I'm going to use one of the many techniques that I can find in the literature. This is called the maximum a posteriori, and there is a lot of text here. I'm not going to describe every detail here. I'm just going to tell you that the solution or the maximum a posteriori estimate X will be based on 3 elements: the measurements, which is this vector Y, the observation matrix that contains information of the geometry of the problem, and this XPR, which is a physical model that I know in advance, I know beforehand of the solution. So this model can be or cannot be similar to the estimate. So that is something that we are going to test in our simulations. So now, additionally, we have some sigmas covariance matrices. And the idea of this statistical analysis with maximum a posteriori is that we are going to include statistical information of each variable into the reconstruction. So I just want to mention what is going to be included in this sigma Y. This sigma Y includes the knowledge that we have about the measurements. As I said before, the measurements are a counting process. So we know that it will have a Poisson distributed noise on it. So that Poisson distribution is somehow included in this sigma Y. In the case of the sigma PR, which corresponds to the prior, in this sigma PR, we're including 2 properties. One of them is we are imposing a smoothness to the solution, and also we are going to include information about the structure that should be transmitted to the final solution. So once we have this information, we can have the Y, L, and XPR. We can estimate the 3-dimensional emissivities, which is this SMAP. So now I'm going to explain what is this prior. For this prior, we have used a parametric model developed by Jorgensen et al. 2019. This model is based on functional forms that are trying to simulate the emissivity of the MHD model. This model developed by Jorgensen is providing me specifically and directly emissivities, not hydrogen, not ions, it's just the emissivities, and is plotted in this column. So this column is similar to what I showed you before. Here in the first column, I have the ground truth in the ecliptic plane and the meridional plane. This is what we want to reconstruct. The prior is this reference based on the model of Jorgensen in the ecliptic plane and meridional plane. And also, because I'm going to do the estimation in this spherical grid, I have the versions for the spherical grid, the versions for each of them, the ground truth and the prior. And I have these names here just to identify them. So the super index indicate that this is it comes from the rectangular grid, and the subindex indicates that this is the ground truth. This is for the prior, and similar analysis is done here. Also, I want just to point out that the prior and the ground truth are significantly different in both structure and emissivity values. So you can observe here that the higher values here are around 510 to the minus 5, while the values in this region are 110 to the minus 4. So the prior is much smaller, probably less than the half, and also the structure, the location of the magnetopause is quite different. So that is challenging for our technique, and we want to test if we can still use this prior to do the reconstruction of the ground truth. Now I'm going to go to the last part of my presentation, which is the experiment analysis. So for this, I'm going to recall that the LEXI orbit has a circular orbit with radius 60 RE. The acquisition period takes around 6 days. LEXI will have a robotic gimbal that will allow LEXI to point over the same position for those 6 days. So that pointing direction in this case will be 8.5 in the X direction and 0, 0 for Y and X RE. The LEXI imager will have this field of view, this pixel resolution, and this number of pixels. And the integration time, as I said before, it's going to be 10 minutes. Now, what I want to investigate is what is the best position in which LEXI can take data and it can reconstruct the three-dimensional structure of the soft X-ray emissivities. For that, I'm going to do 24 experiments. These are 8 experiments for 8 different positions. And you can observe here, I have divided these 6 days uniformly into 8 different locations. And what I'm showing here is the location of the satellite in this red dot, the initial angle, and for each position, we're going to take 2 images, 4 images, or 6 images. So that it's going to multiply the number of experiments by 3, giving a total of 24. But also, we are considering a realistic scenario, so the images are not going to be taken in the exact position. The sensor will be moving for 10 minutes, which is integration time, and that movement represents 0.08 degrees along the circular orbit. So also these 2, 4, and 6 images that we're going to consider here represents a reconstruction that will take 20 minutes, 40 minutes, and 60 minutes reconstruction. And this is related to what I mentioned before, that we don't want to have, or we want to have a reconstruction that takes the smaller number of images to identify the dynamics that can occur in less than 1 hour. So now for each experiment, I'm going to repeat 50 times. And that is because in every time that I have images, I'm going to contaminate them with post-hoc noise. So in order to make a statistical analysis, I have to repeat the experiment with other images with other noise, with other random noise. So I will repeat this analysis 50 times. And the way in which I'm going to do the process of the tomographic reconstruction is, first, I'm going to generate the synthetic measurements using the ground truth in the rectangular grid and the observation matrix, the corresponding observation matrix for the rectangular grid. And I'm going to go in this direction, and I will have my measurements. I'm going to include the noise and the PSF, the convolution with the PSF to estimate the noisy measurements. And then I'm going to use those noisy measurements with the observation matrix in the spherical grid to estimate the emissivities. And for that, I'm going to use the prior that I showed with you in a previous slide. So that process is going to be done. And finally, I have the results for several experiments. Here I'm just going to show you for 2. I'm going to show you this for 2 experiments. I have experiment 1 and experiment 16. The experiment 1 is using only 2 images. The initial angle is 39. The integration time per image is 10 minutes. And in this plot, what I'm showing you in this column, I'm showing you the line of sight density for the equatorial plane and the meridional plane. This is providing me information about the coverage. The white regions means that those voxels, they have no line of sight passing through them, and the colors here indicates how many line of sights are passing through the voxels. This provides me information about not only the coverage, but also what is the expected reconstruction and where I'm going to have a good reconstruction and where definitely I'm not going to have a good reconstruction. So I have this plot for the equatorial plane and the meridional plane. And here I'm showing you the reconstruction. So as I said, I have done this experiment number one. I ran this experiment number one 50 times. I'm showing you just the reconstruction of one of those. And this is the typical result that we can observe. As you can see, the entire magnetosheath cannot be reconstructed, mainly because the observation, the field of view is not covering the entire structure of the magnetosheath. Therefore, we are not expecting to have a good reconstruction. And also, I should say that those regions that are not seen by the sensor are going to be, or are going to use the prior to have a reconstruction. They're going to use the values of the structure of the prior to have certain values. So as I mentioned before, the prior has a much smaller values than the ground truth. So I'm showing here the reconstruction in the equatorial plane as well as in the meridional plane. Now, I have done the analysis of the 50 simulations and the analysis of the emissivities along the sun-Earth line. And here I have three plots. The first one in blue is the ground truth. So this is what we should expect to have. The reference, the black one, is the emissivities, again, along the sun-Earth line. The red line in the center is the mean of the 50 reconstructions for this experiment. And the red shaded region is the standard deviation. So the 50 simulations are located within this region with high probability. Now, as we can see, even that the mean deviates from the reference, which is let's say a good result in terms of using data. The data is modifying the result from the reference. Is not enough to obtain the structure of the ground truth. Now, when we do the experiment number 16, and in this experiment, we have a different initial angle, which is 87.7 degrees. The results, well, this is showing the results with a similar or identical format that this experiment one, and we can directly go to see the results in the sun-Earth line. You can observe that the result, the mean, is deviated significantly from the reference and is trying to follow the ground truth structure. However, it is not the same. And also here I want to point out that one of the main, let's say, processes that are affecting the reconstruction is the inclusion of the PSF. The PSF decreases the intensity, but also creates the distortion. The PSF is the point spread function, creates a distortion in the image that finally results in this difference in the intensity and also in the shape. So just by looking at these two results, we can say that the location of the satellite is crucial for the reconstructions as well for the location of the magnetopause. So here I have two more plots. One of them is well, this slide is to assess the tomographic reconstruction. And for this, we're using numerical values, quantitative indexes like the root mean square and the structural similarity index. Both of them are comparisons between the ground truth and the estimate. And in these plots, I'm showing in green the initial angles. The blue numbers indicates the number of images for each experiment, and I have the 24 experiments that I mentioned before. For each experiment, we have 50 results, and those results have passed through the have been used to create this box plot. The box plot is showing the maximum, the minimum. The length of this box indicates the variability in this ensemble of 50 results. The red line here indicates the median, and this red diamond indicates the mean. So, and this gray line indicates the RMSE of the prior with respect to the ground truth. So we are expecting at least to have values that are smaller than the RMSE, than the gray line. And that is happening when we have angles, initial angles, that are close to 90 degrees, or I would say perpendicular to the Sun-Earth line. In the case of the SSIM, we observe that we have a similar result, and we have higher values of SSIM when the sensor is located in a location most perpendicular to the Sun-Earth line again. Finally, here I have the estimation of the Magnetopause location. The technique to do the estimation is quite simple. And once we have the Sun-Earth line emissivity reconstruction, what we do is just to estimate the derivative and look for the higher value of the maximum of the derivative, and then we can identify the Magnetopause. So we have applied that to the reference, we have applied that to the reconstructions, but also we have the real location of the Magnetopause, who was obtained by taking the derivative of the density of the protons. And that location is 8.05. So, and what I'm showing in this plot is the error in the Magnetopause location. So again, the same analysis for each experiment. We have calculated the error of each iteration for each experiment. As I said before, we have 50 iterations, and here we have the means and the medians. Again, the best results are obtained when the sensor is located in these angles perpendicular to the Sun-Earth line. Okay, finally, and just to mention some conclusions, we have developed this technique to estimate the three-dimensional structure of the magnetosheath and to identify the Magnetopause location. Specifically, we have used one high flux of solar wind that produces images in the range of 0 to 30 counts. So this can be used for future missions to design the sensors. And we can say that if we have 30 counts in your image, we can apply this type of reconstruction. Also, we have identified that there is specific positions of LEXI in which we can obtain the best estimation, the best three-dimensional estimation, as well as the best location of the Magnetopause, and that is given in this range, which is close to the, let's say it's perpendicular to the Sun-Earth line. And the future work will include the development of four-dimensional tomographic techniques to estimate the dynamics of the magnetosheath and magnetopause during space weather transients and try to minimize this number of images to probably 1 or even 2. So if you have any questions regarding the technique, you can contact me. And in case you have questions about this mission, so in the LEXI website, you can also find the links as well as the emails of the PI, which is Dr. Ryan Walsh, who is also a co-author in this project. Okay, that's it. Thank you.
All right, thank you, Gonzalo, for a wonderful talk. I do have a quick question. Your results are partially dependent on your reference model.
Yes.
When you fly LEXI, is it possible, instead of using the reference model you have, to use OpenGGCM or one of the other global MHDs as your reference model?
Yes, that is exactly what we are thinking on. In that case, the ground truth is going to be the real magnetosheath in the space. The reference can be calculated by using OpenGGCM or Bataras. And yes, what I showed you here is probably the worst case, and even with the worst reference, we still have let's say, good reconstruction.
Yeah, and so that brings me to my next question then, to follow up quick. Have you looked at doing the similar analysis where the reference model is actually closer to the ground truth to see how well you do at your lower angles when you're not perpendicular? So that if your reference was much better, how much does that improve your worst images at, say, 30 degrees?
Yes, we have done that analysis. I didn't quantify the percentage of improvement, but yes, I probably will include that analysis in a report to show that improvement.
Okay, excellent. Thank you. Very cool. So I'd like to thank Gonzalo and Nithin again for 2 wonderful talks. Our next set of speakers will be Bea Bea and Mike Shunko, and they will be discussing the GEM focus group mesoscale interactions. Bea will be giving a review of her focus group, and Mike Shunko will be giving an overview of his ASI Python library. We'll hope to see everyone next week for those talks, and I hope everyone has a wonderful week. Thank you again, Gonzalo and Nithin.
Thank you.